Okay, hello everyone. We continue our lecture course, and today, as I promised last time, we start a new topic which is related to contact properties of metal semiconductor, and in particular surface characteristics in general, because surface as an indispensable part of any semiconductor sample or interface of any semiconductor device should be considered with a lot of care, because it defines the properties of this device and defines how this contact metal semiconductor operates as some ohmic contact which has low resistance and symmetric current voltage characteristic, or it is some rectifying junction between metal and semiconductor called Schottky junction. It possesses voltage dependent resistance, and also it possesses not symmetric current voltage characteristics. So the conductivity of the such junction depends on the polarity of external bias which is applied to this system metal semiconductor. So we will consider today the most important band parameters of a semiconductor which are relevant for this topic. Focus our attention specifically on work function, and afterward we'll consider some examples of different metals semiconductor contacts which result in ohmic or rectifying contacts of metal with semiconductor. So let us first consider some key band parameters, and this will look the following. So let me switch here. So we will have top of the valence band, bottom of the conduction band. Let's assume we have N-type semiconductor. So our Fermi energy level is located closer to the bottom of the conduction band. And here we will mark some so-called vacuum energy level. So vacuum energy level is used in order to show that if by any reason electron from a solid body, in particular semiconductor, makes a transition to this vacuum level, we assume that there is zero potential energy of electron with the bulk of the material, and this electron becomes free. So we clearly know what is this parameter. So any suggestions? It's energy band gap, EG. What about this gap between bottom of the conduction band and vacuum level? Have you ever met such definition of this energy? So, I mean, this is conduction, bottom of the conduction band, but the energy between the bottom of conduction band and like the energy gap and the vacuum level is called affinity to electron. Some affinity to electron, and this is, well, let us come back a bit later to this. There is one more parameter which is very important for semiconductor devices, and actually one of the dominant. There is energy gap between Fermi level and vacuum level. So how this energy gap is called?
Ionization potential.
Ionization potential also exists, but this is this energy. It's between the top of valence band and vacuum level, which defines how much energy we need to put to the system in order to transfer electrons from the top of the valence band to vacuum level, means to literally extract electron from the semiconductor. However, this has different name, so let's call this one ionization potential, and this is W, work function. So work function is the energy gap between Fermi energy and vacuum energy. So this we definitely, all these characteristics you need to remember, because you cannot make many step further in semiconductor devices, so you definitely need to understand and remember these definitions. So now my question will be, what is your point of view? Which parameters are features of the material, or the semiconductor material, and which are not, between these four parameters which we have?
Work function is a parameter.
So what work function, what is that?
The energy, the work that needs to be done to put the electrons on the surface of the...
Well, that is affinity of electron, because electrons are kind of on the bottom of the conduction band, so that's definition of affinity. But so we know definition of work function is the energy gap between Fermi energy level and the vacuum level. However, I repeat my question. Which of these four parameters are features of the material itself? Features of the semiconductor material? Energy band gap, yes.
And work function, maybe this.
So, other suggestions? Energy band gap, that is for sure, because it is defined by the type of atoms and crystalline lattice which is formed in the semiconductor material, for sure. That is also true for ionization potential and affinity of electron. However, work function, as you see from the definition, it's energy gap between the Fermi level and vacuum level. And what can cause shift of this Fermi level position? Doping, exactly. So if we add more n-type doping, this Fermi level will come closer to the bottom of the conduction band. If we go for p-type doping, it will go up here, closer to the bottom, top of the valence band. So means that this parameter, like position of Fermi energy, is not a feature of material, because regardless of this small amount of doping which we add, some less than % of atoms, we still have the same material. We don't change material, but we change quite drastically the position of Fermi level. Means automatically that this work function will also change, because it counts from the position of Fermi level to the vacuum level. Means that work function is not a feature of semiconductor material. It like fundamental property. It's just the energy which characterizes equilibrium state of charge carriers in this semiconductor. And based on doping conditions, this equilibrium can be quite different. So that you also keep in mind. because when we have some band diagrams of some, let's say, metal semiconductor junction, we need to remember that all parameters which are fundamental properties of the semiconductor material, they should remain not changed, regardless of any band bending. So they should, at each point, at each cross section, they should be the same. However, work function, like because of position of Fermi level, that is not fundamental property of semiconductor and strongly depends on the doping processes. So, okay, now let us focus our attention on this parameter work function. From general physics course, you should hear about such effect as thermal ionic emission, when we have thermal excitation of electrons and they leave the material because of high temperature, so they transform this kinetic energy of the chaotic motion in the crystalline lattice into overcoming this potential barrier which keeps them inside the material. So the current density for such process would be defined by the following equation. So it's 4 pi times q effective mass of electron times it's k squared divided by h cubed, and here is t squared exponent, here minus E vacuum minus Fermi energy position divided by kT. So that can be represented in more compact form, which probably you remember from general physics course. It's A Richardson constant times t square exponent, and we already know that energy gap between vacuum level and Fermi energy is work function. So we can put here W minus W divided by kT. So the amount of electrons which leave the surface of semiconductor or metal or like some solid state per unit time per unit area is this current density. And that is happening because of internal kinetic energy transformed into like work done against potential energy, which keeps this electron in the solid state. And of course, two parameters here are dominant: this temperature, which defines this kinetic energy which electrons possess, and work function of the material. So now, as we said that work function is not a property of a fundamental property of the semiconductor material, it depends on doping. So it would be good to define work function for different cases, for intrinsic semiconductor, for P and N-type dope semiconductor. So for intrinsic semiconductor, we can write that it is affinity of electron plus 1/2 of the band gap, because for intrinsic semiconductor, if we show it here, E C E V, this is the middle of the band gap, EI, for intrinsic semiconductor. So it should be located close to there, but in order to be more precise, we also need to take into account the ratio between effective masses of electrons and holes. So we have one more term here. It's kT divided by 2 times natural logarithm of effective mass of electron. Sorry, it's electron and here effective mass of hole. So that is like temperature, describes also temperature dependence of the position of Fermi energy within the band gap for intrinsic semiconductor, and as a result it also defines temperature dependence of the work function of an intrinsic semiconductor. So obviously we deal quite often with doped semiconductors, so in that case work function of n-type semiconductor can be expressed as affinity of electron, means this gap, plus depth of the Fermi energy location with respect to the bottom of the conduction band. So in that case we should put kT times natural logarithm of NC, effective density of states, divided by ND. ND stands for concentration of acceptor type doping centers. Obviously here we assume that all these doping centers, n-type doping centers, are thermally activated at given temperature, so all of them contribute to the doping of the semiconductor material. Similar we can write for p-type semiconductor. That will be affinity to electron plus EG, like band gap, and minus depth of the position of Fermi energy level with respect to the top of the valence band. So that will be kT natural logarithm of NV, effective density of states at the top of valence band, times divided by NA, which is sorry, in the first I made a mistake. So it's ND is concentration of donor centers because of n-type doping, so they provide electron. And for p-type, Na stands for concentration of acceptor centers. Assuming again that all of them are ionized at given temperature at which we consider it. Most likely that temperature will be 300 Kelvin, something around room temperature. So now the question will be, from your feeling, so if we pick up silicon, for instance, like the same material, N and P type, in which case we will have larger work function? For P-type, because we have Fermi energy level located deeper for P-type semiconductor, is located closer to the top of the valence band. Okay, so now when we know some already have some background about key energy parameters like band parameters of the semiconductor, we can proceed to the next step, and that is the first moment at this course when we consider not just the semiconductor itself, but also a combination, a contact between semiconductor and a metal. So we have two materials in contact with each other. So let's assume that we have isolated at the beginning metal and semiconductor. So we have Fermi energy for metal. For metal we don't show valence and conduction band because they overlap with each other, so the only thing what matters is Fermi energy. Here we have, let's draw here vacuum level. So this will be work function for a metal. Let's call it M, WM. Then also we have some semiconductor. In our case, for consistency, let us consider N-type semiconductor. So what do we need for semiconductor? We need the band structure. So let it be something like this. Will be E C. Here will be EF, and here is EV. So this will be work function of the semiconductor, WS. They are isolated from each other, not in contact. Let's assume that we put them together and they go into intimate contact. From the point of view of this thermo-ionic emission, some current which flows out from the sample, flow of electrons because of their kinetic energy. What do you think will happen when we put these guys together? We have flows from both sides, because definitely some electrons will go out from the metal and some electrons will go out from the semiconductor. However, what we need to care is the net current, the net exchange of electrons between these two materials. So, from your point of view, in which direction will be the net flux of electrons? Looking at this energy diagram. That it means from metal to semiconductor. So net I need to underline. So it's difference between two, and what is dominant, that is the net flux. So you remember that J, this current of thermo-ionic emission, is proportional to exponent minus W divided by KT, where W is larger, work function is larger. In metal. Means, according to this, since we have here minus, the flux of electrons per unit time will be larger from semiconductor than from the metal. Means if we take a difference between these fluxes, there will be some net residual, resulting flux from metal to the semiconductor. So when this happens, what will actually go on inside at this interface? We will start to build up some space charge in the negative space charge formed by this excessive electrons, which net flux of electrons from semiconductor to the metal. So these excessive electrons will form some negative space charge at the pre-interface region in the metal. It will be quite narrow region because concentration of charge carriers in metal are very high in any way. However, there will be some excessive electrons. If, according to this conservation of electric charge, if we build up some space charge in this metal layer next to the interface, means that there should be some lack of electrons in the semiconductor. If we have some lack of electrons in the semiconductor, that should cause presence of some uncompensated, positively charged donor centers in the crystalline lattice of semiconductor. So initially, in this neutral case of the semiconductor, when we have it before the contact with the metal, obviously the charge of this semiconductor, total net charge, is equal to 0. If part of electrons are gone, then at the interface we will get some positive charges associated with immobilized donor centers in the crystalline lattice. They will just be not compensated by electrons because they are gone. What happens if we have some space charges, positive and negative? What happens in the vicinity to these charges? Obviously, they create some electric field. So they create internal electric field, and its direction will be pointed in such way, so it will go from semiconductor, because they will have positive charges, to metal, where we have negative charges. The vector of electric field will be pointed to, and its direction will be in that way that it will prevent further of this net flux of electrons from semiconductor to metal. So it will be kind of counterbalancing this net flux in order to make it reduce it, and eventually these space charges, positive in semiconductor, negative in the metal, will build up until that moment when we get a balance between equilibrium condition between electron flux from the metal and electron flux from the semiconductor. So electron flux from the metal, by definition, because of large work function, was small. So there was large flux of electrons from semiconductor to the metal. But because of this internal electric field which is induced, this flux will be reduced. So there will be some potential barrier for electrons to move from anti-semiconductor to metal. And eventually, with the help of this potential barrier, we will reduce the flux of electrons from semiconductor to metal to that extent that they will become equal, and there will be thermal equilibrium, which by definition also means that Fermi energy level for metal and semiconductor should be the same. So when systems with charge carriers are in equilibrium, thermal equilibrium, there should be the same Fermi energy level for both systems. So now, taking this all into account, let us consider how will look the band diagram of such contact with metal work function larger than the work function of semiconductor of n-type. So what we actually have here on this image. So now we know that Fermi energy should be the same. So let me probably go to another slide so we don't overcrowd it. We have Fermi energy the same for both. Then here let's consider we have interface. It's where metal and semiconductor contact. So this we will mark for metal area. And there will be some band bending in the semiconductor. So at some distance from this interface, nothing will happen, because we will need only some amount of electrons to move from semiconductor to metal in order to build this space charge, and that space charge at some point will be enough to make enough strong electric field to reach equilibrium, thermal equilibrium. So that means that all these processes are happening in the quite thin layer next to the interface. Deeper in the bulk of the semiconductor, nothing is going on. So we actually have here just so-called neutral region as it was before. We have EC. This is our Fermi energy, and this is our valence band. So as we had it before the contact, the same we have here. Nothing happens. However, at the interface, because of internal electric field, that internal we have linear distribution of electric field. We will calculate all this in details when we discuss p-n junction. Here, we just phenomenologically need to understand the processes what are happening in the interface. So we have electric field, and this electric field will create some band bending at the interface. Something like this. So if we show here vacuum level, it will be flat also in the neutral region of the semiconductor, and it will repeat band bending in the so-called depletion region. We will explain why this is depletion region. So in order to finish with this vacuum level, why we have band bending of vacuum level? Because intuitively it may sound not reasonable, because vacuum level is vacuum level, why it should change. But we should change it because as I said the affinity to electron is the fundamental property of the material. And in the neutral or in this depleted region, we have the same material. We didn't change the material there. So it means this gap should be the same Xi as in the neutral region. Otherwise, if we don't have band bending of the vacuum level, then this Xi will be different, and that will be not real case, because that will require to have some linear change of materials composition, which doesn't happen. So now, because of this band bending, as you see, if you consider here an electron in the neutral region of the semiconductor in the conduction band, there will be potential barrier with a height Q VBI. VBI stands for built-in voltage. This potential barrier will be like band bending is symmetrical, so it will be the same here, will be Q VBI, and the same will be here, Q VBI. So the question will be, what is the height of this potential barrier? So Q times VBI, so we have Q is elementary charge, Q times voltage gives us energy, so it's potential barrier. What it will be equal to? And the answer to this question is actually the difference in work function. So you can take a closer look later when you have time and think about this material. You will definitely see that difference in work function between metal and semiconductor, they give us the height of this potential barrier. So in this case, it will be, we can delete this question mark, it will be V like W metal minus W semiconductor. So now we need to look a bit closer to concentration of charge carriers as a function of position. Let's consider that we have some axis X here. This will be 0, our interface between metal and semiconductor. We remember from previous discussions that equilibrium charge carrier concentration, in this case we're talking about electrons in the conduction band, it will be equal to NC, effective density of states at the bottom of the conduction band, times exponent minus EC minus EF divided by KT. So that is the equation which gives us concentration of charge carriers. We see that we have very strong exponential dependence of equilibrium charge carrier concentration on the gap between between the bottom of the conduction band and position of the Fermi energy level. And we also see that this is actually a function of X. It's changing. So here it is, let's mark it some delta in the neutral part of the semiconductor, the depth of the Fermi energy position in the semiconductor, let's mark it delta. And here at x equal to 0, it will be already delta plus this height of the potential barrier. It will be QVBI. Since we have exponential dependence on this gap between Fermi energy level and the bottom of the conduction band, concentration will be dramatically different in the neutral region and at the interface between metal and semiconductor. So where will be higher concentration of electrons? At the interface, what will be? Why?
Because the electric field.
Here you should not think about electric field, but even with electric field, we mentioned at the beginning that the origin of this electric field is the fact that electrons from semiconductor went to metal, and what is left? Positively charged donor atoms fixed in the crystalline lattice. Means that we have in the area next to the interface, we should have less mobile electrons because part of them has moved to the metal. So that from the thinking of this point of view of net charge flux and also electric field. But also you can look at this equation. So here is minus. So the larger this gap between Fermi energy and bottom of the conduction band, the smaller concentration of charge carriers will be. So if here we have much larger gap, means that here we will have much less free electrons which can participate in charge transport than we have in the neutral part of semiconductor. So actually it was, the answer to my question was opposite. The higher concentration is in neutral region and lower concentration is closer. The closer we reach to the interface, the smaller x is. The lower concentration of free electrons we observe there.
On the interface, it will be higher for positive charge.
That is also true. So we are going to that point. So now, so far, we were talking about electrons. For electrons, is true what I said. But what you are saying is true for holes, which are minority charge carriers. Indeed, you're right, because we can write also for P naught, it will be NV times exponent minus EF minus EV divided by KT. So this gap between Fermi energy and top of the valence band is much smaller in comparison to the neutral region of the semiconductor. However, in this case, we still have larger distance between this energy top of the valence band to Fermi energy than from Fermi energy to the bottom of the conduction band. And this concentration of minority charge carriers does increase, but for most cases when we don't have extremely strong band bending, that is negligible factor. But it can be not negligible factor. If we imagine that we bend more, so we have something like this. So it was n-type here in the neutral region. So this is n-type. Because Fermi energy is much closer to the bottom of the conduction band, but it becomes p-type at the metal-semiconductor interface. So in the case of very strong band bending, we can create so-called inverse type conductivity layer at this junction. But at this point, we are not talking about such strong band bending, but keep in mind that this is a possible scenario. It all will depend how much we bend our bands next to the interface. And with simple approach to this question, it will be how different are work functions of metal and semiconductor, which we put together. So, if we have less mobile charge carriers in this region next to the interface between metal and semiconductor, that means that we kind of deplete this region of semiconductor by majority charge carriers. Majority charge carriers define how conductive this material is, because conductivity is a function of charge carrier concentration. So if we deplete this layer by majority charge carriers, which actually is the reason for the name of this region, is depletion region. That's why it's called depletion region, because it's depleted by majority charge carriers. We have less majority charge carriers in this layer in comparison to the neutral region of the semiconductor. The resistance, or electrical, let's stick with electrical conductivity. Electrical conductivity of this layer will be lower than the neutral specific electrical conductivity of the neutral part of the semiconductor. Means that the resistance for the total resistance of this junction, metal-semiconductor junction, will be defined completely by the resistance of this depletion region. And it will be much higher than the semiconductor itself in the neutral region. Means that we will have high resistance, which already doesn't fit to requirements for ohmic contact at the interface between metal and semiconductor. We will have highly resistive layer, this depleted layer. Moreover, the thickness of this layer will depend on the applied external bias. So when we apply forward bias, when we reduce potential barrier for electrons, so it means that we apply negative potential to semiconductor and positive to metal. So external electric field goes in the opposite direction to the internal electric field. That means forward bias. We reduce potential barrier and we make the depletion layer thickness smaller. Or there is a possibility of reverse bias. When we increase by external electric field, internal electric field, we increase the thickness of the depletion layer and we increase the resistance of this junction, because the depletion layer becomes thicker and it contributes more towards the total resistance of this junction. So which type of contact this behavior reminds you? Is it ohmic contact or rectifying contact? Ohmic contact should not possess high resistance and should not show any strong dependence of resistance on voltage. Definitely all this what I described to you is a signature of a rectifying metal semiconductor junction. So when we form by band bending a depletion layer in semiconductor, that is the rectifying junction. That is the so-called Schottky junction or metal semiconductor junction. And its JV curve, current voltage characteristic, we will definitely spend time to do all quantitative analysis of current voltage characteristic of a diode based on PN junction. But here you can just believe me that current voltage characteristic of such a rectifying junction metal semiconductor contact with depletion region at the interface will look like this. So here will be voltage and current, and in the forward direction it will conduct electricity at some forward bias, small forward bias, and at reverse bias it will remain very, very small. So that is totally opposite to what we expect from a good ohmic contact, and good ohmic contact should be just a straight line with small resistance. So now we discussed the question about rectifying metal semiconductor contact. Let's see how we can make an ohmic contact without this depletion region. So for ohmic contact, we will need to find a little bit either different metal or different semiconductor. So let us assume that here is Fermi energy for metal, and here is Fermi energy for semiconductor. So they are at some point isolated also, but in this case you can show here vacuum level, vacuum, EV, EF, semiconductor. This is EV, this is EC, and this is EF metal. So here is work function of metal. Here is work function of semiconductor, sorry, here. Now the key difference between the previous example, we have work function of metal larger than the work function of semiconductor. Since this is changed, what will happen when we put it together? Again, the question is about this net flux of electrons. Oh, actually no. It's the same. Okay, never mind. I was thinking about different, but it's the same. No, so let me change this. Never mind. So here should be just shifted it downwards. This will be something let's put here. Here is Fermi energy level, and here is valence band. EV, EFS, and this is EC. Okay, now work function of the semiconductor is larger, so it will be finally opposite from the previous case.
Excuse me, when you draw this E vacuum, it means it's inside of a vacuum chamber, or what does it mean?
It just means that at this energy level, it's some abstract energy level, means that at this energy, if charge carrier is moved to this energy level, it's not bound to semiconductor or metal anymore, like bulk of this material. So it just becomes a free electron without effect of crystalline lattice of the material on it. So that is just to show that we get electron out from the semiconductor or metal. So work function of semiconductor is larger than work function of metal. Net flux, how it will be oriented now. So last time you remember that it was going from metal to, from semiconductor to metal. Now obviously it will go in the opposite direction because work function of metal is smaller. So we will have electrons coming, like some net flux of electrons coming from metal to semiconductor. These electrons will create some space charge in the semiconductor, but that will be already negative space charge, and in the metal it will be some positive space charge at the interface when we put it together. Electric field now will be in opposite direction. In previous case it was oriented from semiconductor to metal. Now it will be from metal to semiconductor, and obviously this will cause band bending. In the previous case it was upwards, now it will be downwards. So let us consider such a junction. We have again thermal equilibrium. We have the same Fermi energy, EF. Then we have, this will be our interface. Here is the metal. Here will be our bottom of the conduction band, EC. Here will be top of the valence band, EV. And probably let me put it a little bit higher. This can stay, this we will put just a little bit higher. And here will happen band bending. So this is the region of the space charge. Now, this gap in the neutral region between the bottom of the conduction band and Fermi energy is delta, and this here we can show it. This is our band bending, which is also Q times VBI, and also this height of the band bending will be determined by the difference of work function of metal and semiconductor. So now it's delta here in the neutral region, but for coordinate x equal to 0, this will be very small, and it will be delta minus Q times VBI. So what does it mean? That in this case, according to the equations for equilibrium charge carrier concentration, the gap between Fermi energy level and the bottom of the conduction band will be smaller than in the case of neutral region of the semiconductor, and concentration of free charge carriers, electrons in this case, will be much higher. So that is in line with the equation for equilibrium charge carrier concentration, and also in line with our discussion that work function is larger of semiconductor. That's why net flux of electrons will go from the metal to the semiconductor, means we will gain some electrons from metal in our semiconductor. So there will be more electrons in the region next to the interface between metal and semiconductor. Now, if we apply some bias, we will either further increase band bending, which means we will increase charge carrier concentration, or make this band bending a little bit smaller. However, it will be still there will be still some band bending, and the distance between Fermi energy and the bottom of the conduction band will be smaller than in the neutral region. Means, doesn't matter what we are doing in terms of applying external electric field, external bias to this junction, the resistance of this pre-surface layer will be smaller always than the resistance of the neutral region of the rest of the semiconductor sample. Means that such a contact will possess, first of all, small resistance, because this resistance will be much smaller in comparison to neutral region of the semiconductor, since we have much higher concentration of free electrons. And on top of that, there will be small bias dependence of such resistance. So in this case, when we have N-type semiconductor and we want to create an ohmic contact, we want to find a metal which possesses like work function smaller than the work function of the semiconductor. If we want to make a rectifying junction, Schottky junction, in the opposite, we need to find a metal with work function larger than the work function of the semiconductor. So in that case, these processes of charge transport change direction. That results in different polarities of space charges which are formed in semiconductor and metal, and depends on polarities, we get either upwards or downwards band bending of bands in the semiconductor, which leads us to either a depleted region by majority charge carriers, high resistance and high external bias dependence of the resistance of this depletion region, or in the contrary, we get in opposite case, we get increased concentration of free electrons, low resistance, and weak dependence of external bias. So kind of not a big difference, just manipulate with work functions of different metals and the same semiconductor, but you see how fundamentally different result eventually, which fundamentally different result we get at the output. That makes a huge difference depending what you want to achieve by introducing this metal-semiconductor interface into your device. Yes?
We saw that for the rectifying junction, the depletion layer would be big because there will be high resistance in the depletion layer. But for the ohmic contacts, where we have this, we expect that the depletion layer should be.
So, well, it's not depletion. That's a thing, that there is no depletion in this case because we kind of enrich the layer with electrons. So we make higher concentration of electrons, so we cannot talk about depletion region. We can talk about region of the space charge, because we put electrons inside semiconductors. These electrons create negative space charge. The thickness of this space charge will be comparable to the thickness of the depletion region, or in other words, also space charge, but in first case we had positive space charge. Now we have negative space charge. And the polarity of these space charges defines where bands will go. So in the first case they were up, going up further from Fermi energy, means we depleted by majority charge carriers. Here they go closer, down, closer to the Fermi energy, and that results in the increase of concentration of charge carriers. Why we don't see strong dependence of this thickness of the of this enriched region on external bias? Because voltage drop happens over larger resistance. So what is larger? If we have metal, okay, we can neglect with metal. Metal obviously is very conductive. So first case, we have depletion region and neutral semiconductor. Neutral semiconductor possesses much higher conductivity than depletion region. If we apply some external bias, so we have kind of two resistors. One is very big, another is very small. Obviously, that voltage drop will happen completely almost completely over the large resistor, because contribution of very small resistor voltage drop will be negligible. So that's why when we apply external bias, we can manipulate with the thickness of the depletion region. If we are talking about second case, when we have enriched region by majority charge carriers, then we have opposite case. We have big resistor, which is neutral region, and very small resistor. We apply external bias, voltage drop happens over neutral region of the semiconductor, and eventually nothing happens with the enriched region, because voltage drop there is negligibly small. So when we change in one direction bias polarities and we change polarity in another direction, doesn't matter. The resistance is much smaller in any way in comparison to neutral region, and these changes of the band bending will be negligible. And that results in this nice linear current voltage characteristic, which satisfies requirements for ohmic contact, which purpose is only to collect charge carriers from inside semiconductor and put them into external circuit, or in the opposite, to inject from external circuit into the semiconductor device stack. It doesn't mean that rectifying JV curve doesn't look nice. It just depends what you want. So, but ohmic contacts you will deal with them in any way. Any semiconductor device, you will have an ohmic contact because you need to inject or extract charge carriers somehow. So that is indispensable part of any device. And the key to make such high quality ohmic contact is to create this enriched layer with by majority charge carriers at the interface between metal and semiconductor. For that purpose, you need to pick up proper materials with the ratio of work functions, which will lead eventually to such formation of such enriched layer by majority charge carriers. Okay, so with this we are done. And another thing which we definitely need to consider is surface recombination. So how much time do we have still?
7 minutes.
7 minutes. Okay, so I believe we will discuss surface recombination next time together with already introduction to formation of a p-n junction. Just short explanation, so we don't spend time next lecture on this. It is obvious that at interface or at the surface of semiconductor, there could be some impurities, defects, and so on. So these impurities and defects can create energy levels, deep or shallow energy levels within the band gap. So if we have some deep energy levels created at the interface, they can facilitate the so-called trap-assisted or shock-lead hole recombination. However, we need to remember the features of this interface, the fact that we have band bending at the interface. So that should be taken into account when we derive equations for surface recombination. Also, we at the surface not bulk, so we need to operate not with bulk concentration of defects or impurities, but with surface concentration, means per cubic, not per cubic centimeter, but per square centimeter. So all these factors should be taken into account together with band bending, and based on that, we need to modify this shock-lead hole statistics for trap-assisted recombination, which we derived not so long ago, in order to address these features of those specific conditions at the interface or on the surface of semiconductor. So that will be our goal in terms of understanding surface recombination. After that, we will start to discuss p-n junction. That will be definitely one of the most important chapter covered by this course, because that is, as I mentioned at the beginning of our lectures, in the introduction, it's a building block, and we will really focus a lot on the quantitative description of all processes of formation of p-n junction and derivation of expressions for current voltage characteristics of a p-n junction. Okay, then thank you very much for attention. If you have questions, you're welcome. If not, then see you next time.